Okay, so this is going to be the second part of the Bentel lecture, chapter 4. We're going to pick up where we left off. We're going to look at dose calculation for multiple beams with equal weightings. Most of the time, what you're going to see are not the APPA or even a single beam type calculation. What you're going to end up seeing as far as plans go are several different beams trying to come together conformally, and they're trying to produce a homogeneous dose. Usually the easiest way to put these things together are using isocentric techniques. However, what we're going to be looking at here, we're going to assume a fixed SSD technique, which nobody really does, but for calculations right here, this is what we're going to do. So composite isodose distributions are calculated, and the dose is usually prescribed at an isodose line that encompasses the target volume. So in this example, it's assumed that we've got 4 equally weighted fields, almost like a 4-field box. Each field is going to be 10 by 15. The SSD is going to be 80, and we're going to use a Cobalt 60 unit. Why? Because this was written well before the turn of the millennium. So it's going to be used to deliver treatment. The dose rate, the reference dose rate at Dmax for a 10 by 10 field is 114 centigrade per minute. And the area factor is 1.035. It is above 1 because you're looking at a field that is larger than the reference field. The prescribed dose is 200 centigrade at the 190% line, and it says figure 4.3. So this is what we're looking at. The 190% line is right here. Since the Dmax dose is the same for all 4 fields, and the combined percent depth dose, 190%, is the result of 4 100% Dmax doses, it is acceptable to assume that 1/4 of 190% is delivered from each field. That, of course, is not true for all points along the isodose line, but for the sake of calculations, this is the way we're going to approach it. So the average percent depth dose in a multiple field treatment plan can be found from the total percent depth dose isodose line divided by the number of 100% Dmax doses. So the required treatment time per field can be found from one of 2 methods. The treatment time per field is equal to the prescribed dose divided by the percent isodose line divided by the dose rate divided by the area factor. In this particular case, 200 is our dose. We've got the 190% isodose line, we've got our dose rate, and we've got our area factor. It is again multiplied by 100 up here because this is the PDD, 190, which if we convert that to a decimal would be the same as 1.9, and we'd axe that 100 up there at the top. So that is going to be the treatment time per field, 0.89 minutes per field. Or another way to do this is the prescribed dose per field. So you figure if they're all equally weighted, you've got 4 fields, you're going to take that 200 centigrade and you're going to cut it into 4ths. When you do that, you end up with 50. So that's going to be your prescribed dose per field. And again, if you take that 190% and you cut it into 4 as well, since everybody's contributing a 4th, you come up with 47.5. So you've got 47.5 times 114 times 1.035, basically the same thing as what you got here. But you're cutting this in half because you're looking at it by field, or cutting this by 4, since you're looking at it as 1 field out of 4. And the same thing here. The dose per field is found from either Dmax dose or the dose per field by the average PDD. Either way you look at this, you come up with the same amount of dose. I guess we didn't finish this off. And so your amount of time here is 0.89 minutes per field, or 53 seconds. It seems to me it's a little harder to look at it this way, but I understand why they're doing that. So let's take a look at this particular diagram. We've got 4 equally weighted beams normalized to 100% at D max of each field, which is what's going on here. And it results in a total percent depth dose of 190% as indicated. So if you were to go through and if you were to look up for each individual field and try to find the PDD around here, you'd be looking at something at around, let's see, what did it say, 47.5% or 0.475. The same field arrangement is used on the right, but here 2 of the fields are weighted twice as heavy as the other 2. So you're contributing 2/3 of the weight with both of these beams, and then the other third is divided between these 2. What generally happens in a case like that is that you are you're kind of increasing the dose being delivered here through the patient laterally, and that's going to take your box and it's going to squish it down a little bit. It also tends to raise up the percent, the hotspot percent as well. The combined Dmax dose required for this treatment. Oh, wait, I'm sorry. The next variation of the previous example, the same treatment is delivered, but it is assumed that 2 fields are weighted twice as heavy as the other 2, which is what we just got through describing. The prescribed dose is 200 centigrade at the 205% line. The dose Dmax, the total Dmax dose for all the fields combined is still 400%, but is now distributed so that 2 fields are given 1/3 each and the other 2 1/6 each of the combined maximum dose. So the combined Dmax dose required for this treatment is found from the total Dmax dose is equal to the prescribed dose divided by the average PDD. The average PDD is the isodose line divided by the number of 100% Dmax doses. In this particular case, the isodose line is 205, which is what was decided here, divided by 4, since you've got 4 beams delivering dose at Dmax, or 51.3%. And the combined Dmax dose is 200 times 100 divided by 51.3, basically converting this to a decimal. So you end up with 390 centigrade. So if you split that out, 2 of the fields are going to end up with 130 centigrade each, and 2 of the other 2 fields are going to get 1/6 of that, which is going to be 65 gray each. In this particular example, the total percent depth dose is higher than in the plan, using equally weighting because the 2 fields with the heavier weighting deliver a higher PDD than the other 2 fields. So in the following example, a slightly different approach is used. A patient is treated for carcinoma of the pancreas using a 3-field technique. The interior field is 12 by 8 with a small corner of the field blocked out. The right and the right and left lateral fields are 8 by 8, and a 30-degree wedge is used in each field. All fields are treated with at 80 cm SSD using a 4 MV photon beam. The average field is weighted by a factor of 2 and each lateral field by a factor of 1. So in other words, this is going to be delivering 50%, and these other 2 are going to be delivering 25% of the dose each. So the prescribed dose is 200 centigrade along the 230% isodose line. The treatment plan was calculated by entering 200% at Dmax of the anterior field and 100% for each of the lateral fields. The average percent depth dose is equal to 230 divided by 4. That's our isodose line we want to deliver it to. We have four let's see, I guess the weighting is such that we are looking at dividing this by 4 since we have Dmax at that. Then hang on a second. Number of 100% Dmax doses, and I guess if we have 200% here, that counts twice. It's okay. So then we have 57.5% of each 100% Dmax entrance dose. The combined Dmax dose is therefore 200 times 100 divided by 57.5 or 348. 2/4 or 1/2 of this dose is delivered via the anterior field. 1/4 of the dose at Dmax is delivered using the lateral fields. This is our MU equation here. So we have the dose rate, or basically our prescription dose, what we want to deliver, divided by our calibration factor, and then the tray factor, and then the wedge factor. Since we have no wedge up here, but we do have a little corner of the total field being blocked out, then our factor here becomes 1.0 for the, our tray factor here is 0.96. Those factors I would have to give to you, I think, because I don't think it's actually spelled out anywhere up here. That value would have to be given to you. Same thing for the wedge factor. And then this is our calibration factor here. So we're going to take the AP dose, which is 174 centigrade. We're going to divide that by each of these factors, and this becomes the number of monitor units. For the lateral fields, we have the amount of dose that's being delivered. And then we have our factor here, which again is something that is going to have to be given. Otherwise, this problem doesn't make any sense. And then we've got these fields that are unblocked, but we do have a wedge. So again, this factor is going to have to be given to you. Once all of those factors are given, then we can go through, do the multiplication, and we can figure out that's 125. So the method used in accomplishing desired weighting becomes very important in calculation of the average percent depth dose at the prescribed isodose line. The average percent depth dose is found by dividing the PDD of the isodose line by the number of 100% Dmax doses and not by the number of fields. I think that's a bit more of a confusing way to look at this, but that is in fact what the material is trying to describe. Extended distance. This is something that always complicates matters. It is assumed that a single field is used to treat a 6x40 cm field at 100 cm SSD. The reason you use the extended distances is because you simply cannot fit all of the anatomy that you want to treat in at say an SSD of 100 or whatever you normally set it to. So you have to go through and you have to figure out exactly what you're going to do in order to be able to treat this. This is usually the case for a lot of femurs, in which you want to include all of the length there as possible. One way you can do that is you start backing up the machine away from the patient a certain distance in order to be able to get everything included in the field. So we're going to take a 6x40 cm field at 100 cm SSD. The prescribed dose is 200 centigrade Dmax using a Cobalt 60. The dose rate for a 10 by 10 field is 114 centigrade at 80. Area factor for a 6 by 40 cm field is 1.03. The dose decreases inversely with the square of the distance, so it's necessary to use the inverse square factor. So the equipment was calibrated at 100 plus the reference depth, and the distance at which this is treated is the SSD plus the reference depth. So the calibration was done at 80.5 because your Cobalt unit is going to be calibrated at 80 plus the reference depth, which is 0.5. Using the inverse square factor in order to account for this, we know that we're going to have to basically pump up the amount of treatment time because we're further away from the patient. But because we've moved a certain distance away from the patient, which is an additional 20 centimeters, we have to go through and we have to use the inverse square law. We can't just multiply it by a ratio and not square it, because that's not how X-rays behave. So when we apply the inverse square factor here, we come up with 0.6416. Our equation down here is going to be the prescribed dose divided by the dose rate times the area factor times the inverse square factor. So we take 200 divided by our calibration factor, and then we've got the factor here for the weirder than 10 by 10 field, and then the inverse square factor. Multiplying all that out, we come up with 2.65 minutes. If you go through and if you don't use the inverse square factor, what this comes up with is a 1.7. And so remember that whenever you back away from the patient, that you have to account for that. And the way you account for that is the inverse square law. And that means you're going to have the machine run for longer. So what we're building towards here is a monitor unit calculation that starts to have more and more factors here in the denominator in order to be able to account for certain things that impede the dose and cause what you would normally experience there to be less than what you need in order to be able to deliver that particular dose. So we know what our calibration factor is here. How deep are we going into the patient? We have to account for that. Are we using a tray? If we are, that's going to occlude or stop some of the dose. So we're going to have to keep the machine on for a little longer. Do we have a wedge? If we have a wedge, again, that's going to occlude the dose a little bit. So we have to account for that. Inverse square factor. Are we setting it up at the calibration distance, or are we backing away from that? If we are, then since the dose cuts off at a square value, then we have to account for that. All of these little things we have to start accounting for, and it's just a whole bunch of fun. So now, fixed source to axis distance technique, or SAD treatments. This is where we're going to get into using TAERs, TPRs, and TMRs. If we're going to do a dose calculation for parallel opposed beams with equal weighting, then generally we're going to be looking at an isocentric technique. Since the dose through the volume is relatively uniform, it is customary to place the isocenter at mid-depth between the two entry points, kind of like what you saw in the first video. This requires measurement of the patient thickness or diameter in the direction of the beam at the central axis. The isocenter is then set by subtracting 1/2 of the patient's diameter from the SAD. In a patient who is 22 centimeters in diameter, using a therapy machine with 100 cm SAD, the SSD would be obviously 100 minus 11 because you're setting it up in the middle, at least for these examples. Rotating the gantry 180 degrees would result in 89 cm SSD for the opposing field because in this example, you're trying to set it at midline. So Cobalt 60 beams, we're going to assume that for this example, a treatment delivered via equally weighted parallel opposed fields uses the Cobalt 60 machine. The fields are 17 by 17 cm and the patient's diameter is 18 cm. The reference dose rate without the patient present for a 10 by 10 field is going to be 109 centigrade per minute. Area factor for a 17 by 17 field is 1.056. You'll notice it's actually a number that's a little bit higher than what we've seen before, and that's because a 17 by 17 is going to allow more scatter radiation in than a 10 by 10. The TAR at 9 cm depth is 0.799. That is something we can look up at the table, table A.3. Prescription is going to be 200 centigrade to be delivered at mid-depth. So the treatment time is found from taking the prescribed dose and dividing by that whole list of factors that I was talking about. Reference dose rate, your area factor, and the TAR. And remember, the tissue to air ratio is basically a ratio of what you're measuring in the air and divided by what you see in the phantom. I believe that's right.